This lesson is about projectiles launched at an angle and some of the details of their motion. By the end of it, I'm hoping you'll be able to calculate the velocity of a projectile both at the top of its flight and as it's landing. I hope you'll understand a little bit about the shape of that flight, and I hope you'll understand a little bit more about how angle relates to how far an object goes. So I'm going to put that video into Tracker, and I'm going to use Tracker to get screenshots of where the ball is at different times. So here's what you see if you do that. It's obviously a beautiful look at the trajectory of the ball, but there's something else really important that's going on here, and we could see that by looking at the relative heights of the ball at different times. I'm going to draw some lines on this picture to make this more clear. So if you look at the ball at this time and this time, which is basically one frame before and after the peak, it's at the same height. It's also like that 2 frames after and 2 frames before, or 3 frames before and after, or 4 frames before and after. So at equal amounts of time before and after the peak, the ball is at the same height. And that implies a really deep symmetry in the speeds of the projectile as it flies through the air. Let's take a look at why. It's important to remember that our horizontal velocity time graph is constant. We never see the horizontal velocity changing because there's no horizontal forces. The acceleration is 0. The vertical velocity time graph is linear. This is v equals VO plus AT. And there's a slope of negative 9.8. Because this is linear, the velocity on the way up decreases the same amount every time period. And then on the way back down, it increases by that exact same amount every time period. So if we were going to look at what the velocity of the ball is as it flies through the air, if we just look at the real velocity, which would be these blue arrows, we kind of miss the pattern. Clearly, the velocity decreases to a minimum and gets as flat as possible, and then it increases back again and gets as down as possible. But if we look at the components of the velocity, I think we really see what's going on. The horizontal velocity in red never changes because there's no horizontal force. So that component stays constant. But the vertical velocity shrinks to 0. We know from before that when you throw something straight up and down, the velocity at the top is 0. It's not quite true with a projectile thrown at an angle. It's still moving horizontally at the top, but its vertical velocity has shrunk to 0. Because of this linear dependence vertical velocity has on time, it then grows back in exactly the same way that it was lost on the way up. And that's the reason for this symmetry. There's one other thing worth noting too. Because Vx doesn't change the entire flight, Vox is Vx, and because Voy shrinks and then grows back the same amount when you get back to the same height, if a projectile lands at the height it was launched from, it will be going the same speed it was launched. So that's kind of an interesting thing. Sort of interesting for understanding why it hurts to catch a really hard hit baseball even if you're very far away. It also should be very good evidence that you should never ever ever fire a firearm up in the air, because it's going to come back down at the same speed it was launched with. Alright, so here's another two-dimensional launch example problem, and I'll go through part A fairly quickly since we've seen one already. But notice in part B it asks a question we haven't seen before. How high does it go? So let's take a look at the solution. Part A, pretty similar to how we solve all of these problems. We start by making our picture. For this type of problem where it lands at the same height, usually it's best to call the origin the launch point, because that makes 3 of our 4 distances 0. Remember, in an entirely different picture, you take the non-horizontal velocity and you make it into the hypotenuse of a triangle, and you use sine and cosine to find VOY and VOX. And just be careful as you copy into the table, you get things in the right place. Of course, AX and AY are still what they always are. So, solve an equation for one of the dimensions, in this case y, find time, plug into the other, you get how far it goes. What do you know about the maximum height for this? Well, not much. It's not a triangle, we can't use SOHCAHTOA or anything to find it. This is a parabolic shape. But one thing we do know is that at the top of the flight, the y velocity has decreased to 0. So unlike in one-dimensional motion, it's still moving up there. But in the y dimension, it's not. So we can use Vy equals 0 and one of the 2 equations that has Vy in it to solve for information about the top of the flight. So anyway, we have Vy equals 0. Now we can use one of our equations that involves Vy. In this case, it's asking for height, so this was the appropriate one. And now we know how high it goes. So it's important to remember that Vx and Vy, we haven't used them a lot, but we still can use our intuition about them at different points in the problem to figure out about a projectile's motion. Here's a final problem that really shows how we might have to use final velocities to answer the question. So this one says we have a cannon whose muzzle is 3.7 meters above the ground. It's at a 31-degree angle, and it wants to know how far the ball goes and what speed and direction it has when it lands. It launches at 65 meters per second. So this is a tricky problem, but the first part is in some ways very similar to what we've done so far. There's just one thing that's a little different. It's launching and landing at a different height. So I think we go back to what we did with horizontal launch problems. We call the origin directly under the launch point. And that means we know the coordinates of where it launches, and we're trying to find x, the horizontal distance it lands at. After that point, it's pretty similar to what we've done. We do a triangle. We break the initial velocity into components. When we fill out our table, though, one thing that's a little different is that both y and yo are not 0. So when you start to put down your y equation, it's impossible to cancel out t the way we have been. So all we can do at that point is a quadratic equation to solve for t. So it might be a good idea to review how to do that, and we can practice that in class if you need to. Once you find t, though, plug into the x equation like you usually would. So this goes 387 meters. What angle is it pointing at when it's landing, and how fast is it going when it's landing? Well, its velocity is going to be down like this. And the easiest way to figure it out is to solve for Vx and Vy. So here's what that looks like. So I just did 2 instances of the V equals VO plus AT equation, and I found Vx and Vy that way, using the time I had solved for in the previous part of the problem. Now, in order to combine them back into what the real velocity is, the hypotenuse of this triangle, we can use the Pythagorean theorem. So if I do that, I get a final velocity of 65.55 meters. And then we can even find the angle that this is at using an inverse trig function. So theta, this interior angle, tan theta is going to be 34.5 over 55.7. So that's what I do here. And I end up getting the angle 31.8 below the horizontal. When you report angles, you have to be a little bit careful what angle they're asking for. You also could be being asked what this angle is, the angle from the x-axis. But typically I'm going to ask you what the interior angle is. And make sure you have some reference of what that's an angle from. So one interesting question in projectile motion is, how does launch angle affect how far a projectile actually goes? So what we're going to do in this problem, we're going to make the assumption that we're launching a ball and having it land at the same height it was caught from. That'll keep the problem relatively simple, and we can really just focus on the effect on angle. So we're going to say a baseball player hits a ball at 35 meters per second. How far does it go? And different parts of the class will be assigned different angles, 15, 30, 45, 60, and 75 degrees. So I'm going to now go through and solve this problem as an example. I'm going to pick 30 degrees as my example, but you may not have the 30. You may be assigned one of the other angles. After that, we'll take a look at what patterns we can see in the data, and we'll try to come up with a rationale behind any patterns. So as we always do when we're solving problems like this, we should really start with a picture. So like I said, I'm going to do an angle of 30 degrees. And we're going to have a ball go up and come back down. So this is going to be 0, 0, where we launch, and where we land is going to be x, 0. So that's going to be the picture I use to get distances. The picture I use to get velocities, entirely different. We're going to visualize our launch velocity, VO, 35 meters per second, as the hypotenuse of a triangle. And the part of that velocity that's horizontal and the part of vertical, we can get just by finding the sides of that triangle, VOX and VOY. So what we need to do is basically take the sine and cosine of 30 degrees, and that ought to get us VOX and VOY, because the sine of 30 will be VOY over 35, and the cosine of 30 will be VOX over 35. So I'm going to just quickly solve for what VOY and VOX are. 30 sine is 0.5 times 35. That means VOY is 17.5. And 30 cosine times 35. VOX is 30.31. So the next step is going to be to make our table. And we'll just copy our information that we've gotten from doing the trig and from drawing our first picture. A lot of what we're looking at are zeros. X is unknown. VOX is 30.31. VOY is 17.5. As almost always, we have no horizontal acceleration, and we have the acceleration of gravity vertically. So we're good there. And I think basically now we just solve an equation, one for horizontal, one for vertical. So I'll start with horizontal. So X is going to be equal to 30.31 T. So we'll do vertical. So 0 equals 17.5 T minus 4.9 T squared, because 1/2 times 9.8. So solving that out quickly, we'll divide through by T. Oops, that's not a squared anymore. So 4.9 T is 17.5. Okay, so t is going to be 3.57. Which I now can plug into here. So x is 108.25 meters. And I forgot to fill in my table. VOX I said was 30.31 meters per second, and VOY was 17.5 meters per second. All right, so let's take a look at what all of the data looks like. So if you do it all out, you get kind of a remarkable symmetry. 15, 30, 45. We actually grow how far it goes as you get to a 45-degree angle. And then it shrinks again. And strangely enough, when you get to 60, you get the exact same distance that you got with 30. When you get to 75, you get the same distance you got with 15. Hopefully you recognize the relationship 15 and 75 have, and 30 and 60. They are complementary angles. So basically, the reason for this is the sine of one of them is the cosine of the other one. And because of this, we see that there's actually a trade-off in horizontal and vertical velocities. At 15 degrees, we have a really fast horizontal velocity, but a really slow vertical. And they're flip-flopped when you get to 75. So it almost seems like the best solution is to have as much fair sharing between horizontal and vertical as possible, which is what we have with 45. Why would that matter? Well, if a ball is going to fly through the air, there's two things that matter. You want it to go fast over the ground, so VOX you want to be as high as you possibly can. So that would make us think that like 15 was the best solution. But the problem is it's not in the air for very long. So even though it's going wicked fast, it hits the ground so quick, it doesn't go that far. So the other extreme would be 75. In the case of 75, you're kind of not moving very far left and right, but you're in the air for a super long time. So you have a long time to travel. So that's why you end up going the same as 15. So this trade-off between horizontal velocity and time is actually really important. You want to have as much of both as you possibly can. That's what gets you the farthest distance. Beyond what, oh, these are some sample calculations. I've actually gone through all of them, so you can check on Flickr and check your work if you need to. This is really beyond the scope of this course, but all I did here is I used letters for everything. I didn't actually plug in any numbers, and you could sort of see why having a fair sharing between x and y is so important. If you solve your y equation for time, you get this. If you plug it into your x equation, you end up with this. And basically, you've got the sine of theta and the cosine of theta in this final equation. And you need to get both of those numbers as big as possible. And the only place you can do that is at 45 degrees. If you have any angle less than 45 degrees, cosine of theta is too big and sine of theta is too small. If you have any angle more than 45 degrees, it's the opposite. Cosine of theta is too small, sine of theta is too big. 45 is the compromise. There was a lot in this video, so I want to summarize it. Hopefully you saw that the y velocity is symmetrical throughout the flight. The positive y velocity decreases to 0 and then increases to a negative version of the velocity as you go through the flight. Interestingly enough, it's going to land at exactly the same speed it was launched from, because Vy will now be the opposite of Voy, and Vox will be the same. We learned that we can use Vy equals 0 at the top to solve for anything we need to about the ball when it gets to the top. And we learned we can find a final velocity by combining Vx and Vy. We also learned that the maximum range of a projectile will happen when that launch angle is 45 degrees, which is a compromise between velocity and the two dimensions.